In this video, we'll discuss the kinetic energy an object has when it's rolling. We learned that there are two ways of modeling rolling motion. We can model it as a combination of translational and rotational motion, or we could model it as purely rotational motion with the axis of rotation being located at the point P that's in contact with the ground. We're going to focus on this second model as we derive an expression for the kinetic energy of a rolling object. So according to a stationary observer, someone who's off to the side, the kinetic energy of this wheel, of this rolling object, would be equal to 1/2 I omega squared. Because again, we're modeling it as just rotation, so we'd only have rotational kinetic energy. This would be the moment of inertia about our axis of rotation, which is located at point P. This axis of rotation does not pass through the center of mass. So we have to use the parallel axis theorem to be able to calculate that moment of inertia. And the parallel axis theorem says that the moment of inertia about point P would be equal to the moment of inertia about the center of mass plus md squared. In this case, our d would be equal to the radius of my object. So I have I of the center of mass plus mr squared. I'm going to plug that into my kinetic energy expression here. So kinetic energy is equal to 1/2 times the quantity, the moment of inertia about the center of mass, plus mr squared times omega. Then I'm going to go ahead and distribute my terms. So I have 1/2 times the moment of inertia of the center of mass times omega squared plus 1/2 mr squared omega squared. Now I'm assuming here my object is rolling smoothly. And we learned that when something is rolling smoothly, the velocity can be expressed as the angular velocity times the radius. That means that the radius squared times the angular velocity squared would simply be equal to the linear velocity squared, which means my kinetic energy could be expressed as 1/2 times the moment of inertia times omega squared plus 1/2 mv squared. We know this to be the rotational kinetic energy and this to be our translational kinetic energy. So this is just proof that when an object is rolling, it has both rotational and translational kinetic energy. That means that when you look at a problem where we have an object such as the solid brass ball rolling along a track, that when we're focusing on conservation of energy, we need to remember that our object has both translational and rotational kinetic energy at any point where it's moving. Your goal is to complete this problem, to find what is h if the ball is on the verge of leaving the track when it reaches the top of the loop, and if the ball is released at a height of h, which is equal to 6 times the radius of my loop, what's the magnitude and direction of the horizontal force component acting on the ball when it reaches point Q? Bring your answer to class and we'll discuss it.